particular system or any particular solution, right? My whole idea have some sort of a thought experiment on what we need to do in order to unlock both real-time and near real-time querying on top of Lakehouse. So this is by no means a novel concept. There's a lot of solutions that are there that does this today. But what I want to focus on is how we would want to do this on a Lakehouse native way. And even on Lakehouse, there are a lot of solutions that does this today. And I want to dive deep into what are all the solutions that does this, what are all the trade-offs those solutions have, what are the pain points, and more importantly, open up some thought or some food for thought on how we can take inspirations from other systems that we can plug on top of Lakehouse to get better performance, right? So none of this is novel concept. None of this is an implemented system. So it's basically about analyzing some of the existing systems, what challenges they face, and what inspirations we can take from some other systems in a completely different industry, right? That is how we as an industry can evolve, right? That's the whole idea of this talk. So agenda, like quickly clarify, what do I mean by real-time and near real-time? Some assumptions, what can we do today? What are the pain points and fundamental gaps? And last, some food for thought, as in what inspirations we can take from other systems. So context setting, right? Real-time and near real-time buzzword, it means one thing in one industry, whereas something else in a completely different industry. If you take high frequency trading, then it's like microsecond is what you talk about real time. And less than 10 milliseconds, actually it considers near real time and not real time. But on the other end of the spectrum, if you take climate forecasting, even 15 minutes is good enough to be considered as a real time. So we want to align on what do we mean by real time here, right? I think for the sake of this discussion, we can take the middle ground, ride hailing, delivery, and maybe even card and payments fraud. So let's say that anything less than a second, we can consider to be a real time, and anything less than 5 seconds, we can consider to be a near real time, right? If this is the assumption, then what can we do today? Where do we fall short? And what can we do differently to be better, right? That's the whole idea. As I said, let's align on some numbers, some terminologies. By hot data, I mean any data that is less than 500 milliseconds from the point of ingestion. Warm data is less than 5 seconds, and cold data rest, right? And since we are talking about Lakehouse, anything that we discuss should be able to do on a petabyte scale, right? It should be Lakehouse supported, right? That is the most important part, because if we take that out of the picture, there are already a lot of systems today that actually does this. So the question is, how do we do this on top of Lakehouse? Some metrics, obviously the first one is event to ingest insight latency. I mean, it's self-explanatory, right? The most important thing that we are worried about is like from the point we see the event till the point we derive analytics out of the event, that is the latency that we are talking about. And we want that to be either less than 1 second in case of real time or less than 5 seconds in case of near real time. Two sub-metrics, obviously. Query speed, obviously your query engine should be able to query fast. And the other part is query engine should be able to query the data that is less than 1 second old. So the freshness of the data also matters. Only if both of these things come together will we be able to achieve like real-time and near real-time querying capabilities, right? Now, very briefly, what can we do today? I'm not going into details of all these systems because, as I said, we have a lot of systems today, right? On top of Lakehouse itself, we have a lot. Like, I've actually mentioned some of this here, but I think we also saw few other systems during the talk. For example, Kafka's table flow, right? Apache Pymon is, I wouldn't say a new project, but new to the open source ecosystem. I think it was open sourced last year. It has its own unique take on how it can combine both ingestion and querying and provide like sub 5 seconds or even in some cases sub 1 second query results. We have Delta Lake's continuous mode. I don't think it's on par with the rest of the systems out there, but I'm just noting a few of these things, all to drive the point that this is not a new concept. We also have few non-Lakehouse based things, Snowpipe, ClickHouse that we saw, where both compute and storage are together, right? each has its own architectures, right? We can achieve quite a bit of these things today. Apart from this, we can also hand roll our own ingestion and querying layer. Like we can use Flink, we can consume data from whatever streams that we want, we can integrate that with some sort of a query engine, and then try to come up with near real-time analytics. But then those solutions fall short the moment you think about petabyte scale, right? Like it's really, really difficult to compress both hot data as well as cold data and combine real-time answers to it. So this is what we can do. And I'll, as I said, I just glossed over it, right? Now we go into the deep parts of it. Like, what are the pain points of some of these systems? Some pain points are already solved by these systems, but the idea is to give a picture of what complexities can arise by trying to solve this problem, right? Obviously, the very first one, metadata management. Like, as we know, these open table formats like Iceberg, Delta Lake, Hoodie, everything, they store the raw files in S3, but they store additional metadata in separate files. The whole reason is that we don't want to couple both so that we can evolve both of them independently. But then when we talk about real time, when the data volume that is coming into our system is huge, a lot of things goes for a toss. So what Iceberg and other systems does is, whenever you commit something, the commit is a concept where you get a bunch of data, you write the data to S3, and then you update that metadata telling that, hey, Iceberg, I have written new files to this location. That, let's say that is the concept of commit. And if you get a lot of data at a very high speed, there is a limit in which how frequently you can commit to the underlying object storage, in this case S3, right? First of all, S3 has its limitations. Like there's nothing called as free lunch. Obviously, there will be throttling happening even at a partition level in S3 if the rate at which data comes in is very fast, right? So high frequency micro batch writes generate thousands of snapshots, so which means it's a hell managing those things. The other important part is single threaded commit lock. Most of the systems today that writes to these open table formats are predominantly single threaded in nature, primarily because of the fact that you want consistency when updating the metadata. They apply something called as optimistic lock, in which case you don't need to be single threaded, but then again optimistic locking falls short when the rate of ingest is like extremely high, right? All you need to do is like you first check what is the latest version of snapshot, and then when you want to update, you check whether the previous version read is the same as the current latest version. If there is a mismatch, then you just don't write it. But imagine thousands of writes or thousands of commits coming to a single partition. This can very easily happen, right? Query planning overhead. So query engines today often reach out to these metadata stores and catalog on a frequent basis to understand what is it that they are dealing with. Like, what are the schema? What is the structure? How many records are there? They usually collect some statistics like for every column, what is the maximum value? What is the minimum value? They try to gather as much intelligence as possible. And the whole reason is when a new query comes in, instead of scanning the entire data, I think they can provide an optimized plan which limits your table scan. Simply put, there's a lot more optimizations that can be done. But again, so basically, if under heavy load, if the number of manifests file keeps on adding, then query engine now has to go through a lot more files to actually provide you a clear and more performant logical plan. So if you can think about this, none of these things are actual problems in our normal use cases. But as anything with scale, these things starts to break down when the scale increases. When you talk about 5 million events per second ingested into a Kafka topic, and you want to analyze that within 1 second, is that even possible? Like that is what we are trying to analyze here, right? The last one, it's not much of an issue, but catalog catch-up, like these catalogs like Glue, Polaris, etc. What they do is like they also try to be on top of the changes, not as in-depth as the metadata layer, but still on a superficial level. And they also start to fall short when the rate of input massively rises, right? Then the next attribute, small files. I think we spoke about this sometime today. Too many small files is not good. You have to pay a lot of price for I/O, and you cannot buffer a lot of data in memory as well. If you say that, hey, let me buffer the data and write into one big file, but you cannot, because you are getting data at extremely high speed. So 5 million events per second, if you buffer it for 5 seconds, your in-memory capacity should be huge, right? So you cannot buffer the data as well. You need to flush to the disk in order to actually save your compute from going down. But then if you flush to the disk, you will inevitably end up with these small file problems. As I said, object store throttling. Again, very straightforward. I think S3 supports per prefix 5,500 reads per second and 3,500 writes per second. This is per prefix. And it's very common in high throughput scenarios where for a single partition, this rate exceeds, right? So how do we handle that? Compaction overhead, straightforward. Like I think we already saw this here. One approach to tackle these small files is to do periodic compaction, which means behind the scenes, you combine a bunch of small files, put it into a big file, and then tell that the query engine need not scan all the small files. But then even that comes at a cost, right? Like your compaction now needs to be on top of the rate at which your data is coming in. But that's just not possible when you use like huge scale real-time scenarios. Like compaction can only happen on a periodic basis. 1 minute once, 5 minutes once. If you trigger compaction every 1 second once, then that's it, right? You really cannot proceed. Those approaches also have some flaws today. Last one, it's a very minor one. It is very particular to how your data spread is. Let's say you configured Kafka to receive a bunch of events partitioned by a certain key. And for some reason, the partitioning scheme is not consistent. You have hot partitions, which means the data for that particular partition is going to go to the same partition in Iceberg, and that particular partition is going to see a lot of activity, which again means the distribution of data files in Iceberg is going to be completely skewed. This is a very common problem that we see, and the query engines actually have to pay the price if this issue occurs at a very huge volume, at a very high scale, right? Yeah, this is a really nice one, data model, right? See, today, the standard for ingestion is Kafka. Kafka topics are the predominant ways in which you consume events for your analytical workloads. But the way Kafka stores data is on an event-by-event basis. Similar to, if I can consider it as a row-based storage model in RDBMS, Kafka does this on an event-by-event basis. But as we all know, for analytical, columnar is much, much more better, right? Because at any point in time, we are only interested in statistics of a single dimension or a few dimensions. We are never interested in all the properties of a single record, right? So there is this big impedance mismatch in terms of how we consume the data and how we use it for analytics. We will actually see an interesting approach how to solve this. Schema evolution friction, I think we already spoke about this, especially when you talk about, this does not happen very often, but when you talk about scenarios where you pump events from your front-end apps or mobile apps or IoT devices, and the schema for those devices change, the rate at which you pump these events, your catalog, your open table format cannot really catch up with all the schema changes that happens, because schema changes are again nothing but additional data that is captured in the metadata layer so that your query engine can understand it, right? All of these things, as you can see, you will start to see a theme, which is at scale, these things start to break. Exactly once for CDC data, I mean, I don't even want to get started. There's a lot of things that can go wrong when you deal with CDC data, especially if you don't guarantee exactly once scenarios, then that's it. If you don't guarantee consistent ordering, then if you write CDC data into your actual sync, it's going to be completely screwing up the actual representation of the data, right? Because in case of CDC, the order of operations matter. You add, delete, add, that is not the same as add, delete, right? A lot of these things matter. And these are all common problems that are out there which starts to break for scale. Few others. Planner. I think one critical part if you want to achieve really performant queries or query speed is the logical and physical plan that your query engine or compute engine creates. Today, Spark or any other engine, Trino that you take, they know to create a logical plan. First step is to, on a high level, tell, hey, these are the partitions you need to consider. Ignore everything else. These are the files that you need to prune, because planner is aware of the metadata that is behind the scenes, right? But today, any planner or any query engine that you take, they can only talk to Lakehouse systems. Like, they can only talk to the data when it comes to Lake, which is fine, which is solving our problem so far. But if you think about handling millions of records and you want to respond within 1 second, then planners needs to change. They need to start talking not just to the data on Lakehouse, but they should also start talking to the systems that are part of your ingestion pipeline, right? So that is one issue that is not present today. Next is query engine is not ingestion aware. This is same as planner, but the only difference is query engines have this concept of executors where they do the grunt work. Once the planner provides a plan, query engine, the executors in the query engine are the one that goes to S3, reads the files, etc. Even those executors today are only Lakehouse aware. They do not do anything apart from it, right? Like, they do not go to other areas to get more rich data to make their queries performant. Back pressure management, right? I would not attribute this as a big problem, because back pressure management is a better way to signal to your consumer that something is not working. That is not directly related to handling or getting real-time queryability on top of Lakehouse, but whatever system that we are building should have back pressure notification built into it, so that you can send the correct notifications out, right? Cool. I think I kind of finished this in 15 minutes, but that's fine. We will still have the most important part, right? As I said, these are not concrete solutions. My whole idea for presenting this is, hey, we have inspirations that we can take from other systems in other industry, so that we can share what we can do and thereby try to further or enhance the real-time querying capabilities of Lakehouse. So some of these things are already present in few cutting-edge solutions. Some of these things are absolutely not present, and the whole idea is to spark conversations on where these can take us, right? It would be really nice if we can achieve sub 200 milliseconds query latency on top of Lakehouse. Like, fantastic, right? But then, is that even possible? How can we do it? My whole idea is to spark conversations. That's the whole idea. First one, right? Sorry, yeah. Message queue. As I said, this impedance mismatch, right? Kafka has its own way of storing data, but when we consume for analytical workloads, it's completely different, columnar. What if, and there are already solutions that does this, but what if we can reimagine the ingestion layer to actually be columnar native? Today, what's happening? We are collecting a lot of events from IoT devices, mobile devices, all those stateless devices, right? And even those devices, they are not pumping data or pumping events to our backend as soon as they see this. Even within those mobile devices, they do micro batching, because if you just keep on sending data from your mobile phone to Kafka or your backend, your user's bandwidth is going to suffer. So companies optimize that a lot. So they already do some sort of batching over there. The only part, unfortunate part, is that batching happens on a row level. What if you can change that, batch it on a columnar level and send it to your ingestion system, right? You avoid the transformation that you do on a streaming ingestion side, right? But what if, let's say, the mobile apps do column first batching, but again you have to go to Kafka, and Kafka now has a different storage structure. What will you do, right? Here's where we can think about other systems. Recently there was a system open sourced by a company called Webrica. If you know about it, it's called Fluss. Fluss is basically Kafka compatible API message broker system, where you can store the data in column native format, right? Which means there will be small batches of data in Fluss that is like columnar, which again means when you consume the data, you literally have to don't do anything. You don't need to convert a row-based data, like consume 100 records or 1000 records and then convert it into your columnar format. You don't know it. You don't need to do it. That's already given for you, right? So, and Arrow, as we know, has been really making waves in terms of providing efficient data representation across different bandwidths or different boundaries, right? Your representation in memory as well as over the wire is same. So today, a big price that an ingestion system pays is serializing and deserializing data when it has to transfer from one system to another system. You just don't need to do it in case of if you're using Apache Arrow. And what if your mobile apps and IoT devices can send Arrow batches directly from the front end, right? You literally get a lot of things for free. So embrace Arrow IPC format end to end, produce Arrow batches at the source as early as possible. Clients can potentially produce Arrow batches before even reaching the server. And the other important part is when you design your ingestion layer, design it in such a way that it is as much as possible Arrow native. There's almost every query engine today is Arrow compatible. Few query engines are Arrow native. So I think it's in our best interest to actually embrace this concept as Arrow nativity and try to use that throughout our stack, right? Oh, sorry. The next is queryable columnar brokers. So I said planners today reach out to the metadata layer to get some statistics, like how many columns are there, what is the maximum value of a column, what is the minimum value of a column. But that information is available only after the data comes to the lake, only after it is written to S3 or your object storage. What if you can do a minimum or not minimum, a small sized of such a query on top of your message broker itself? What if the Fluss that I just spoke about allows you a way to actually get this metadata for the events that is present in the queue? And guess what? Fluss actually does this. You can get information about metadata information about the data present in a topic at any point in time so that you don't have to wait for the data to arrive at lake, right? If planners can start talking to your ingestion layer, then they can very well combine both the data, the hot data present in your message broker and in your ingestion layer, couple that with your warm and cold data in lake, then you get petabyte scale, but almost near real-time and real-time analytics, right? So provide the ability to directly query the data in the queue to allow pointed lookups. Again, similarly touching upon the previous point, planner awareness, right? So planner should also be able to talk to your ingestion layer to get as much information as possible. Now, if you think about this, at least this particular point, it feels like we have industry specific closed source systems that can do sub-second analytics today. Like high frequency trading has a lot of those systems completely proprietary. What are we doing is like we are decoupling that, making it a much more open one, and then trying to build our abstractions on top of it. Similarly, what one of our friends asked, hey, are we building an RDBMS on top of Iceberg? And if you think about it, the natural progression with any architecture or any software, you first solve a problem. You do the bare minimum necessary to solve a problem, which is what RDBMS. Then comes the problem of scale, at which point you start to see the shortcoming of those solutions. In case of RDBMS, it is very difficult to scale at a very big workloads. So that's where we start to decouple those systems, which is what we are now doing with, not right now, but a couple of years before, we are doing with this Lakehouse. But now, we are again going back a full circle where we are trying to build the same features as RDBMS, but on top of a composable stack, right? And that is the evolution that almost any data stack takes. And if you compare that analogy here, query engines when it started, like Spark, whatever in 2014, 2013, they only spoke with direct data, right? Data in the lake. Now what we are doing is we are splitting it out. We are trying to build composable blocks, but the next step is actually to build abstractions on top of these composable blocks so that we again close the loop. And what's pending today, as far as I know, that is something that is not available, is planners, part of query engines, do not really talk with ingestion system. That is the remaining gap that needs to be closed in order for us to derive like sub-second analytics, right? As soon as the data comes in, if your query engine is aware of it, like what better than that, right? Like you can do fraud analytics. As soon as the user clicks a button in an app, you can do analytics. If you're playing a game, you can do analytics. Some of those are there today, but those analytics are very narrow because they cannot handle petabyte scale, which is what we are trying to solve here, right? Next, watermarking based on queue consumption, right? So this is an interesting one. How much ever I say that, hey, let's do all these things to achieve sub-second query latency, it's an inevitable truth that our ingestion system is going to struggle when you are dealing with millions of events per second. So we need to apply some pragmatic boundaries to tell that from our system's perspective, we are very confident that we have seen events until a certain point in time, and any events that come after that, we are just not going to worry about it, because the generation of events is not under our control. It's under some mobile app, some network, like whatever network coverage that person is using their mobile app, that determines how late a data comes to our backend, right? So we cannot keep dealing with all of those things. So what we need to do is, whenever we see events, we need to start watermarking it, telling that, hey, at any point in system or any point in time, I can give you a guarantee that my query engine gives you a response within 1 second for an event that has arrived at a certain time point. And watermarking is not a new concept, right? Today we can actually do watermarking using Flink, etc. But the point is, you need to do that. Like you need to consume the events from Flink, add this, put it to one more Kafka topic, and then consider it, right? Now, and this again goes back to the strategy of shift left. What if the data that we get in via the broker already has this built in? Then we can basically get that part also for free, right? Thereby shielding us from any events that come late for various reasons. Again, I think this is for the metadata management part. As I said, S3 has its limitations. Any cloud storage is going to have its limitations. They cannot give you free space forever at whatever rate that you want, right? Here we will have to improvise. We have solutions that are object storage compatible, but can be deployed on NVMe and SSD disks, MinIO, right? What we can do is, we can couple our ingestion system to write data to these object storage compatible things, periodically flush it to Lakehouse. See, the whole benefit of Lakehouse is you own your data, right? You should have the freedom to see your underlying data and do whatever you want with it. But when you're talking about real-time systems at 1 second scale, I doubt if people will tell that I want my data within 1 second in Lakehouse and I want my data to be queried on top of Lakehouse. No, that is not the case. You want your data to be queryable within 1 second, but it's okay to have a 5 second or even a 1 minute buffer before the actual data ends up in your Lakehouse. You want to derive analytics, but you want to own the data as well, right? So you can introduce these kind of solutions to circumvent those limitations provided by the cloud storages. Periodically async flushes to object storage to achieve durability. The other interesting thing, I think recently Cloudflare acquired a streaming solution called ArroyoDB, which is more like a in-memory streaming solution, but also has SQL capabilities on top of it. They are like basically experimenting with how can they have ArroyoDB's catalog in edge locations so that wherever your query engines are deployed, you can get metadata about your data much more faster, like sub 5 milliseconds. Like if your data is in your edge, see, first of all, your schema is not going to change very often. If you are talking about 1 million events per second, your schema is not going to change 1 second once, for sure. it's probably going to change at the best case minutes once, or sorry, at the worst case minutes once, or best case hours or days once, right? So you can certainly take the leverage, the flexibility of caching those metadata, all those schema in your edge locations, so that query engine need not go to the actual underlying data lake to actually leverage that information, right? Again, sharded and partition commits. So this is what I said earlier. Open table formats like Iceberg, etc., they do a commit whenever they save something in S3. Whenever they do some, S3 is the example here, object storage. Whenever they do some changes to the underlying data store, they want to update the metadata telling that, hey, I have done so and so changes, please keep track of it. That is called the commit. And if a single partition, basically like a single table, basically gets a lot of data, then that commit process is going to suffer. What we can improvise here is that we can have more fine-grained committing process. The beauty of Iceberg here again is it's a specification. It doesn't dictate you how you do the commits. So for whatever it's worth, you can like build your own committer layer that commits per partition. So this allows you to circumvent the race conditions that happen in a single table level. You will only be paying the price where if there is a single partition that's a hard partition, for that partition you will have to do commits slowly. There is unfortunately no way around it. But having said that, again going back to the fact, Iceberg is a specification. So there is nothing stopping us from creating an in-memory representation of Iceberg today, where it can handle a lot more faster updates to commits, updates to metadata, and your query engine talks to your in-memory representation of the Iceberg metadata, again periodically flush it to S3. But as you can see here, the overall theme is that there's a lot of scope for optimization. All of these things come with their own complexity. None of this is free lunch. But the point is, if we have to have an ambitious goal, then tackling complexity is the most important part. Like we need to form abstractions around this complexity, which makes our lives easier. And none of these things are novel approaches, right? Lot of systems do today. All I'm trying to do is like taking inspirations from different systems and how we can apply this on top of Lakehouse to achieve real-time query. The next is sharded metadata based on data freshness, right? This is an interesting thing. So, as I said, Apache Pymon, they basically, so in case of real-time streaming, where the volume is very high, we spoke about the small file problem, right? A naive approach would be write very small Parquet files into S3, periodically combine them into bigger files, right? What Pymon does is they use LSM trees and basically, they store those small files in a different level storage. They have multiple levels of storage and they basically L0, L1 and L2. The most immediate data goes to L0, and since it is structured in an LSM way, it's much more easier to combine than raw Parquet files. So they do this periodically, and this is less compute intensive compared to compacting Parquet files. Again, the concept is same. You are compacting things periodically, but the difference is the data structure you are using to compact is much more compaction friendly rather than rigid Parquet files, right? So again, introduces complexity, but gives you the benefit of like using the best tool for the job. And the other thing, as I said, is that hot metadata should be in the queue. Warm metadata should be in these kind of compaction-ready data structures, I would say. And then the cold metadata can be in analytics-ready data format, which is again columnar. Wait, sorry. Okay, yeah, this is the last one. This is an interesting one. As I said, query engines today get hold of this metadata by periodically asking the underlying catalog, telling that, hey, give me the columns in this particular table, give me the maximum value and minimum value or number of null values in a particular column, so that they can generate an optimum plan. But if you think about it in case of a data warehouse or a lakehouse, 90% or 95% of your queries are going to be on top of 10% of your tables or 10% of your data sets. So if query engine can leverage that fact and your ingestion layer actually publishes metadata changes to the query engine, then query engine can selectively decide what metadata it needs to listen to, update to. Then this will completely eliminate the fact that query engine needs to periodically poll the underlying catalog to get the metadata, right? All these are small and minor optimizations, but when you talk about scale, it matters a lot, especially if you are talking about a single table that is receiving tens of millions of events per second. This kind of an optimization will give you massive benefits because your query engine need not spend asynchronous periodic compute keeping itself updated on top of the catalog changes. This is an approach. I think some of the, I don't exactly remember the database name, but something by DB2 actually does something like this. I will probably follow it on the name, but this is an interesting approach which can give us a lot of benefits. Storage optimizations, I think I spoke about this already. Use S3 compatible NVMe or SSD storage, periodically flush it. Hot data in NVMe, warm data in LSM, cold data in Iceberg. Yeah, I think, as I said, none of this is foolproof. A lot of these things are abstract thoughts. None of this is novel. But again, the idea is to tell you that there's a lot more optimizations that we can do on top of today's ingestion and query engine systems working on top of Lakehouse to actually eke out more performance. I think my whole idea is to inspire if we can take any one or two of these approaches and start implementing it. And if you see benefits out of it, that is the best. And if you also know of any approaches that I've not covered, but that can help us achieve this goal, I'd be very happy to hear such approaches. So I think with that, I will call it done. Any questions? Correct.
So do you have any views over here that how can we basically improve our ingestion within Docker into access of it, but not standard of it?
I think I'm still not completely hearing it clearly. Can you speak up a bit out?
Yeah, just asking that if it is Docker, I took S3 access of it rather than standard of it. We can also improve the performance because we only would be we only would be relying in a single availability zone rather than multiple availability zone in those single regions. So there we can basically factor out the replication that is there between replicating the data across regions or across multiple data centers within a single region.
So, like, I'll just repeat to make sure I got it correctly. Today, AWS provides the option to write data into directory buckets, S3 tables, not raw buckets. And you're asking about how we can easily replicate to other availability zones or other regions to get better performance. Is that the question?
Yeah.
Yeah, sorry.
So what you're asking is, instead of standard, you might be on the express one and blue it or 100.
Oh, yeah.
Answer is yes. So for 100 ms kind of workloads, 100 ms comes up to 30 ms is what we have seen while taking Kafka events directly to S3. So the answer is absolutely blazingly fast and yes. I just took it from you, sir.
No, I think that's the same answer that I have, right? Obviously, cost is a different thing altogether. But is that your question? Like,
Yeah, I mean, over here we have a trade-off that there is no availability. There is no high availability we get over here.
So see, so you would very rarely come across real-time event storage systems where the purging happens right after you write it on S3 Express. So there are at least a day to 7 days to even larger details that you would see for Kafka. Any of these Kafka distributed Kafka applications that you have today. So even if your S3 Express zone 1 goes down, which I have never heard it went down ever till today. But of course you have to plan for it. You would still have your source data available in Kafka. So it's not that goes away and suddenly you lose, so your data durability is questioned. So the benefit that S3 Express brings in is mostly for applications like diskless Kafka, where you don't write on a disk at all, and you take care, you only write it on storage on CSPs. So there, these kind of solutions come in very, very handy. Cuts down your cost by almost 60-70%. Performance improves by 3x to 5x, 10x. So people kind of love it. But of course, there are case to case. I mean, whether you go for it or not depends on the kind of latency that you're looking for. Even with ST Express, you would have 3-digit latency. 3-digit milliseconds is you can't come out of that.
Thank you. Cool. Then, yeah, if not, no more questions, then thank you for your time. I hope I've managed to add some thoughts, some ideas to your mind, and I would be happy if you can give me some more of your ideas as well, right? So, thank you.